thank you for the introduction, and again, sorry for the delay. So I hope you'll be able to see the slides okay in that way. So I wanted to tell you a little bit about using mixed precision in eigenvalue solvers, and I will concentrate on symmetric eigenvalue problems in this talk because solving the eigenvalue problem using mixed precision it's not easy. So we need to start with the easy case first. And before I start, I'd like to say that it is joint work with my late husband, Nick Higham, Marcus Webb, and my PhD student, Zhengbo Zhou. So it's not working. Okay, it's delayed. Okay. So I would say that most of the work that's been done on mixed precision algorithms for dense eigenvalue problem, it's mainly focused on linear systems and least squares problems. Eigenvalue problems, as I've just said, they are a lot harder to solve using mixed precision because the solution space is much larger. And also, when you want to find the eigenvalues, you can't do that in a finite number of steps. There's an iteration in the background. Right. This is not great. So nowadays we have access, as you can see now, we have access to lots of different precisions. So I've only listed some of them on the table here. So you have we tend to work in double and single precision in a traditional scientific computing, but we also have access to a lower precision nowadays, mainly on GPUs, like a half precision with FP16 and bfloat 16. And that's the Google low precision. So those precisions are mainly used in machine learning applications, neural networks. And then there's also lower precision, FP8, that's mainly used by transformers, and even lower, FP4. But most of the work in scientific computing is done. I don't think I can point there. It's not to work. Okay. It's done in double precision or single precision. And there's something that is worth knowing about, maybe you already know, but the next generation of GPUs, in particular those made by NVIDIA, they are not going to support double precision arithmetic, and maybe also single precision arithmetic in the future. So that is a danger for scientific computing. What are we going to do? We won't be able to exploit their capability. So we need to rethink our algorithms and make the best of all those lower precisions that are available to us. But this is something that we really need to think carefully about. So I won't talk about what we can do. I'm going now to concentrate on eigenvalue problem. But before I do so, it's just not working very well. I'm sorry. I think I'm going to try it that way. No. I wanted to show you this graph here. Okay, so you can see it. It's the energy, the power consumption over time to solve a linear system X is equal to B on the NVIDIA B200 GPU. And I quite like this plot because it shows that, so we're looking at two curves, a blue curve and a green curve. So the blue curve it's solving this linear system using double precision. And the green curve solves the linear system using both half precision and double precision. I'll explain, I'll tell you later how this is done. But what the plot shows is that using a mixed precision allows you to solve the linear system much faster, up to 8 times faster, but also it uses 8 times less power. So making use of that low precision is, I believe, and I think it's quite convincing here, something that we need to aim and very good in terms of reducing the power consumption. So what do I mean by FP16 and FP64? So the output is at FP64. So the output, the solution will have double precision backward error. So both solutions here have the same properties. And this solution here is computed using iterative refinement. So you can do iterative refinement nowadays using a number of different precisions. So here I'm using 3 precision. The precision that I call U, which is the working precision. And then there's a factorization precision, UF. So the F stands, it's really for the factorization. So you do an LU factorization at precision UF. You compute the residual, so you solve that linear system here using this factorization computed at precision UF. I've not said whether it's low or high yet. You solve the linear system at precision, sorry, you compute the residual at precision UR, and then you iterate. So you solve this linear system for the residual and you update. Then again, you use different precision. So you can do that a couple of times or maybe more if needed. Usually once is enough. So usually we use for the factorization a precision that is lower than the precision U. That's the working precision. So you can think as UF as single precision, double precision, and UR would be quadruple precision. It doesn't have to because you've got those less or equal signs here. So Nick Higham and Erin Carson, they worked on this kind of, I mean, there's a lot of people who work on iterative refinements for a linear system, starting with Wilkinson. But I wanted to just show you this table that they've obtained in I think it was 2015, where they were able to list the kind of precision that you need to use for your factorization, your working precision, and the computation of the residual to obtain a normalized error of double precision. So H here stands for half precision, 10 to the minus 14. S stands for single precision, so 10 to the minus 8, and so on. So D is double and Q is quadruple. So you can achieve both double precision, backward error of double precision, component-wise error of double precision, so 10 to the minus 16, and a forward error of 10 to the minus 16 by using iterative refinement in the manner I've just described, when the condition number of the matrix of your linear system is no larger than 10 to the 4. So now if it gets up to 10 to the 8, then you can't really you cannot use a half precision for your factorization. You need to increase the precision to a single precision if you want to guarantee backward errors, component-wise backward errors, and forward error of 10 to the minus 16. So now if you go higher with the condition number of the linear system, then what they found out is that if you solve the within iterative refinement, if you use your factorization to precondition GMRES, and solve the linear system for the residual using GMRS with preconditioning, then you can still guarantee double precision for the backward error, component-wise backward error, and forward error, as long as you use those rules here. So that is very nice. And in particular, this is amazing that you can still solve accurately linear system with very badly conditioned matrices in that manner. So can we do the same for the eigenvalue problem? That's what we're interested in. We don't have a full analysis yet, but we've started to look at a number of algorithms.
And just to be clear, these are non-symmetric matrices.
Yes, in that case, I was just starting with linear systems just to say what we're aiming at. So now I'm going to concentrate on eigenvalue problems with symmetric matrices to start with.
Non-symmetric and partial pivot.
Yes. So can we exploit mixed precision to solve the eigenvalue problem? Yes. But solving the eigenvalue problem, it's much more expensive. So if you have a symmetric matrix to solve the eigenvalue problem for both eigenvalues and eigenvectors, it's about 27 times more expensive in terms of flops compared to solving a symmetric positive definite linear systems. And again, when we want to exploit low precision, it's the NQ part that we aim to do in low precision, because that's where we're going to save time. So for the eigenvalue problem, this is a lot harder to do, and I think it will become clear in a moment. So for years, well, at least for a few years, I thought that it would not be possible to do the N-cube operations entirely in low precision, but that might not be the case anymore. So I always thought that it was unavoidable that some of the N-cube operations would need to be done in working precision, but I'm not convinced that that is true anymore. So if we want to gain any speed up for the eigenvalue problem, the N-cube operations, they will need to be done using blast-free operations. And there are new ways of doing blast-free operations using integer arithmetic with the Ozaki scheme. So that's why I think that that is not true anymore. So what we can do, like for linear systems, is to use low precision to precondition the eigenvalue problem so that it can be solved more quickly. So what are the symmetrical eigensolvers that are available to us nowadays? Well, really, I like to put them into two groups, those that work on a tridiagonalization of the matrix. So you start by tridiagonalizing the matrix first, and then you solve the eigenvalue problem on the tridiagonal matrix using bisection or inverse iteration or multisection and inverse iteration. You can use the multiple relatively robust representation. So that was the work of Beresford-Perlet with Interjit Dillon and also Rosny Marquez. You can use the QR algorithm or the divide and conquer algorithm. And then there are those algorithms that work directly on the initial matrix, like the Jacobi algorithm or the QR-based dynamically weighted ALE algorithm. And Yuji knows a lot about that because he's derived that algorithm. So I'm going to look at both in the next few slides, and then I'll concentrate in particular on the Jacobi algorithm approach. Well, one of the issues with the first approach, the one that consists on the reduction to tridiagonal form, is that the reduction to tridiagonal form, it's really the bottleneck. What comes after can be done fast, but the reduction to tridiagonal form is, in a way, the most expensive part in terms of time and also flops. So what we can do is maybe do the reduction to tri-diagonal form in low precision. So I'll discuss that in a moment. But before I do so, let's look at what happens. So what we can do first is compute an eigenvalue decomposition in low precision and try to refine it. Okay. So we can solve the eigenvalue problem, let's say in a half precision. So L here, think of it as being a half precision. So the eigenvector matrix QL is going to be orthogonal to this low precision, and the residual the relative residual is going to be bounded by n times this low precision. Okay. So we want to use that QL as a preconditioner. We have to be extremely careful, because if we apply it to our matrix A, then we're going to lose a lot of information. It's not going to be an orthogonal similarity transformation to working precision. So you're going to completely, you won't be able to get any accurate eigenvalues in that way. You're losing too much precision. So if you want to use your QL as a preconditioner, you need to do something to it before you can apply it. And you need to orthogonalize it. It needs to be orthogonal to the working precision. So if your working precision is double precision, then you need to orthogonalize your Q. So it's already almost orthogonal, but not quite yet. So you need to orthogonalize it. So that's one approach that that I will discuss in a moment. And another approach consists of refining this eigenvalue decomposition here. And that's something that Davis and Modi had looked at many years ago, and it's been looked at again by Ogita and Eishima more recently. So what is the approach of Ogita and Eishima? So they have this eigenvector matrix that is inexact, and they want to refine it. So they want to compute the exact eigenvector matrix X. And they rewrite it as the approximation plus a perturbation. So it's a multiplicative perturbation here. And then, so they take this equation here, and then they use that iteration. So they want to find EK at each step of their iteration, and that EK solve those two matrix equations here. And they have an efficient way of doing that. But in fact, to find EK, you will need to form this matrix product here and this matrix product here. And that consists of doing 4 matrix multiplication per step. So their iteration consists of making 4 matrix multiplication per step. And it's a Newton scheme. So if you computed your eigenvalue decomposition in single precision, for example, to start with, and you want double precision, then usually you just need 1 or 2 steps. So no more than 8 matrix multiply to get your double precision refined eigenvalue decomposition. So here, should check. Okay, you have this. We have this figure here where we compare the timing of computing the eigenvalue decomposition using the LAPACK code DSYEV. So that's the routine in LAPACK to solve the eigenvalue problem, the symmetric eigenvalue problem. And we compared it to the single precision. So D is for double, S is for single. And then looked at what happened if we do 8 matrix multiply with it. And the two curves are completely superposed. So matrix multiply is so fast that if you do 8 extra 1, it doesn't add any, it adds negligible time to the overall computation. So that's the way to accelerate your code. Okay. So those are just initial experiments, but I think there's a bit more that can be done here. We've not used any GPUs, it's just on CPUs here. So I don't want to talk about that, but there's more work that can be done here to accelerate the eigenvalue problem using this kind of refinement scheme. So what we looked at is using mixed precision together with a preconditioning in the Jacobi algorithm. So in what follows, every time I use pk, that just denotes a polynomial of low degree in M. And we're using 3 precision. So L stands for low precision, U is the working precision, and HUH is the high precision. Okay, so what we want to compute is a spectral decomposition of a symmetric matrix A. And we want the eigenvector matrix Q to be orthogonal to working precision. So what we do is that, so that's not new, that's been looked at before. We compute a preconditioner that is such that it's orthogonal to machine precision, to working precision. And we want the off-diagonal entries to be bounded above by, so the relative error or the off-diagonal entries are bounded above by the low precision standard norm of the matrix. Okay, so if we solve the eigenvalue problem in half precision, then all the half-diagonal entries will be of the order of the half precision standard norm of the initial matrix. Then we compute the precondition matrix. Okay, so we do that computation here, but we do that at a higher precision. And I'll explain later why this is very useful. And then once we've done that, then we demote that high precision to working precision, and we apply the Jacobi algorithm to that matrix A comp here. But that matrix is not diagonal, but it's almost diagonal. Most of the weight is already on the diagonal. The off-diagonal entries have all a magnitude that's extremely small based on this here. Okay? So you just need a few sweeps of the Jacobi algorithm, maybe no more than 2 sweeps. So that's very fast. Okay, so Jacobi, you're already in the quadratic convergence regime of the Jacobi algorithm, so a couple of sweeps usually enough to get convergence. And then after you compute the eigenvectors based on QG and the preconditioning matrix. So this has been looked at before, but what people haven't done before is apply the preconditioning to higher precision. Okay, and that's extremely important if you want to compute eigenvalues to high accuracy. So how to compute the preconditioner? So the way we do it is to first compute an eigenvalue decomposition of the matrix at lower precision. Okay, so that's fast. And then we orthogonalize the eigenvector matrix to precision U, to the working precision U. So you can use modifying Grant-Schmidt, the Newton-Schultz iteration, which is just matrix based, matrix product based, or you can just do a Hausser-Order QR factorization. Another approach consists of doing the tridiagonalization of the matrix A at low precision, because that's the bottleneck. So that's what you use, that's what you do at low precision. Okay, and then you solve the eigenvalue problem for the tridiagonal matrix at working precision, but that's fast. And then to construct your precondition matrix, you apply the Hausser-Order metric, the Hausser-Order vectors to the eigenvector matrix of the tridiagonal matrix. You do that at working precision, because the Hausser-Order vector, you've computed them at low precision, but you can apply them at double precision. It doesn't matter. What you'll get at the end is a matrix that is orthogonal to working precision. It would be an approximation of the eigenvector matrix to low precision, but it will be orthogonal to working precision. So that's the key here. So this plot here, it's just experiments done for using random matrices in MATLAB generated with the round SVD function and condition number of 10 to the 6. And what the plot shows is that all the four algorithms I've just mentioned, they all return matrices with off-diagonal entries of the order that are smaller than the single precision. And surprisingly, for this type of matrices here, using the Haussorter approach, where we do the tridiagonalization in low precision and then the rest in double precision and then reconstruct everything in double precision, that's the one that tends to return off-diagonal entries, the smallest. We don't really understand why yet, but hopefully we'll do soon. So in the early 1990s, Demel and Veselich, they showed that for symmetric positive definite matrices, if you use this stopping criterion in the Jacobi iteration, then the computed eigenvalues, their relative error, is bounded by a polynomial of low degree in n times the working precision times the scale condition number. So the scale condition number is the two-norm condition number of that diagonally scaled matrix A, where you just take the diagonal entries of the matrix and you take their square root and just invert them. Okay, so you have a positive definite matrix, so the diagonal entries, they cannot be 0, so that's well defined. And what they showed is that, I think it's Roy Matas showed that when you have a graded matrix, then the scale condition number here can be much smaller than the two-norm condition number of the original matrix. So they said that the Jacobi algorithm is therefore more accurate than the QR algorithm, but you have to be careful. It's for positive definite matrices that are graded. Okay, so it's quite a small class of matrices for which that is true. So we claim that with our approach, that is true for a much wider class of positive definite matrices, and we were able to show that. So the next slide is quite, it's a busy slide with lots of maths in it, so formula. So I'm just going to maybe go through it slowly. So our results assume that we have a positive, symmetric positive definite matrix that is necessary. We can still apply our algorithm to symmetric matrices, but the results, they only hold for positive definite matrices. Okay, so we compute A tilde is going to be a precondition matrix. A preconditioner is such that it's orthogonal to machine precision. We know how to compute that. I've just shown you not long ago. Then we have those two quantities, gamma h, and I don't know whether you can see my, maybe I should. So we have gamma h and gamma. So gamma h, just think of it as being n times the multiple of the high precision, and gamma is n times the working precision. So we have a number of assumptions, A1, A2, and A3. I don't think that that's working here. Do I need to point it to the... So we have those three assumptions, A1, A2, and A3. They're only there so that our bound is easy to interpret, okay? They're not necessary. They are there because they are useful, they allow us to get a bound in the theorem that is easy to read and interpret, okay? So the condition A1, we use it to, well, it's useful to prove that our precondition matrix is actually positive definite, so we don't use positive definiteness. The second assumption will be useful later to decide which precision to use for a given matrix, and so on. Okay, so what the theorem says is that with our algorithm, so we compute a preconditioner that satisfies this property here. We apply it in higher precision, and then we do a Jacobi on the precondition matrix. Then the computed eigenvalues, they have a relative error that's bounded above by a polynomial of the low degree in n, so degree 3, in fact, times the scale condition number of the precondition matrix. So in the standard Jacobi, you've got the condition number of the scaled matrix. Here it's the condition number of the scaled precondition matrix. And it turns out that this condition number here can be much smaller than the condition number of the scaled original matrix. And then a small multiple of the machine precision. So this is a very nice bound. And then, well, I said cubic, okay, P3 is at most quadratic. What we've been able to show is that if the off-diagonal entries are sufficiently small compared to the diagonal entries of the scaled matrix, of the precondition matrix, then the scale condition number of the precondition matrix is bounded by 3. So here you've got a 3. Okay, so that shows that under that assumption here, when that's the case, at least we can compute the eigenvalues to high accuracy. And that's a much larger set class of matrices than the graded matrices.
So this sort of statement is for all.
Oh, yeah. So when you're in that condition here. So there will be, I'll show later, there are matrices for which, well, in fact, the next table, where that is not small. Okay. So here we've got a number of very ill-conditioned matrices. And the table shows the two-norm condition number of those matrices, so very high. The scale condition number is not much lower, and in some cases it's a bit higher. But our scale condition number of the precondition matrix is usually much lower. In some cases of order 1. So some plots here showing the relative forward error. So here the eigenvalues are ordered from largest to smallest. So we've compared, so MP2 Jacobi is the precondition Jacobi algorithm where the preconditioner is not applied to higher accuracy. MP3 is when it's the precondition Jacobi algorithm where the preconditioner is applied to higher accuracy. So that's the algorithm the previous theorem applied to. Standard Jacobi, so would be yellow, and the purple stars are for MATLAB's AG, and that's those dotted lines here are it's the bound that we derived. Yes, the bound that we derived. Okay. So for the smallest eigenvalues here for that matrix, which is generated with Randes-VD, then the small eigenvalues, no, the large eigenvalues are computed to high relative accuracy. But for all the algorithms except ours, their accuracy decrease as the eigenvalues get smaller, but we can compute them to high relative accuracy. So that's just one example, but that tends to be the case. So here it's another matrix that is a correlation matrix from the any matrix collection. Again, here all the algorithms tend to compute the eigenvalues. I don't know whether you can see my mouse, maybe. Yeah, they tend to be well computed, but as soon as they become too small, then the algorithms fail to compute them to any decent accuracy, I'd say, in that case, whereas we can still compute them to high accuracy. So I don't know how I'm doing in terms of time. Okay. So I still have a few more slides because I've only talked about the eigenvalues, but just let me summarize. So we have this preconditioned Jacobi algorithm that uses 3 precisions. So the preconditioner uses low and working precision to compute it. Then we have the we apply the preconditioner to higher precision, so that's matrix multiplied, and then we do the Jacobi iteration at working precision. And we can prove that the eigenvalues of a wide class of positive definite matrices are computed to high relative accuracy. And also our analysis allows us to choose the precision given the condition number of the matrix. So if we have a quick way to estimate the condition number of the matrix, then that allows us to choose the precision at which to compute, to apply the preconditioner and to also compute it. So that's published in a paper in SciMax. So we've also looked at the one-sided Jacobi algorithm. So what we've done can be extended to the one-sided Jacobi algorithm to compute singular values of a matrix. I don't have a huge amount of time left, but just going to. So what we do is that we use low precision to compute the preconditioner. We apply it to high precision to the matrix. We want to find the singular values. And then we use this Jacobi algorithm to the preconditioned matrix to find the singular value decomposition. So our forward error analysis yields smaller error bounds than any of the singular value decomposition algorithms. And what we recommend to do is that for tall and skinny matrices, so very often for tall and skinny matrices, what we can do is to compute first the QR factorization and apply the Jacobi algorithm to the R factor, okay, because then the R factor is very small. But we do not recommend to do that. The analysis shows that you won't be able to, and our numerical experiments as well, you won't be able to get high accuracy if you do it in that manner. It's best to first precondition the matrix and then apply the compute the QR factorization of the preconditioned matrix. If you do it in that order, then you can guarantee a high relative accuracy. So I just have a couple of slides left. Just very quickly. So here I've got plots showing the relative error for random matrices. We've compared our 3 precision preconditioned Jacobi algorithm to the this code here is the LAPAC one-sided Jacobi algorithm, and this one, the GSV, is the one-sided preconditioned Jacobi algorithm in LAPAC. And we compared also our codes to the MATLAB SVD. Okay. So that's relative error, and we are always much lower than any of those three codes here. So we can compute the eigenvalues to higher precision. Again, another plot showing exactly the same thing. So here, the SVD code does well in MATLAB, the MATLAB SVD code, except maybe for the smallest and largest singular values where it's not so good. But we are always much lower than the, our precision is much better than the other algorithms. In terms of timing, one issue is that we have to use higher precision to apply the preconditioner, and we don't easily have access to fast matrix multiply. So that can be an issue. But here what we've done is that we've compared, we've done the, our working precision is single precision. So we can do double matrix multiply in double precision very fast. And what this plot on the right shows is that our precondition Jacobi is as fast as the Jacobi algorithm in the LAPAC. It's not as fast as the one-sided precondition Jacobi algorithm in LAPAC, but it computes eigenvalues to a much higher accuracy than the other algorithms. So we actually have a mixed precision Jacobi SVD that works pretty fast and is more accurate. Okay, so I'll stop there. Thank you. Yeah.
First one, do I need this? My first question, sorry, I'll just ask one question. You seem to be making quite a lot of the fact that the matrix was symmetric, positive, definite. But for eigenvalue problems, that's really not an issue, is it? Because you just make an identity shift, and you can always make your matrix symmetric, positive, definite. So what changes in the analysis?
Okay, yes, you can do that, but the shift, yeah, you can do that, but you're still shifting your matrix, so you work with a shifting matrix. So at the end, you need to get back to the original matrix.
Yes,
so
if I shift by an exact floating point number, you get no rounding doing one way or the other.
No, that's so that the analysis applies there. Yes, that's right. And we would do that. So for matrices that are very close to being positive definite, we would shift them. That's we do that in numerical linear algebra anyway. Yes, it's a good thing to do, shifting.
I'll just have another quick one. And that's in my area, we're not generally not interested in all the eigenvalues. Generally, we're interested in 1 and 2, and they're eigenvectors. So is there, obviously you could find all of them and then throw the rest away. But is there anything super that you do that doesn't require that?
Yes. So Jack Dongara's got an algorithm that can be used in that context. So you only compute part of the spectrum and you only refine part of the spectrum. In fact, that follows his PhD thesis. It was really on that topic. In fact, Jim Wilkinson collaborated with him on that, and it's been revived and relooked at again to use it with low precision.
Thank you, Fran. But can I make a comment? Is that I always thought that different problems had condition numbers for different reasons. And here you're talking about condition number that I would call the condition number, the solution of a linear system of equations, I guess. When you talk about K2 and so on, right? Whereas the conditioning of eigenvalue problems, I always thought was to do with the gaps between eigenvalues. I don't see that in any of your analysis. Is it hidden somewhere? Or am I just missing it?
So, okay, the condition number for the eigenvalue. So the eigenvalue, the symmetric eigenvalue problem. So the eigenvalues are well conditioned. Okay, so, but in the analysis, then the condition number of the matrix, it does appear. So if you want, so it appears in the bounds, and you do need it. You need.
I guess this is why I was asking if these results true for every k, because if your eigenvalues are very, very close together, then it's harder to find these in general.
Oh yeah, yes, that's correct. So,
I see, but
but the
results still
analysis,
apply.
yeah, the analysis is there, and it shows that, yes, the condition number of the matrix is there. You need to.
We have Yuji who wants to ask a question.
Hello, can you hear me? Hello,
Yes.
Brad. Thank you very much. I was just wondering, how does the runtime breakdown look? Is it dominated by the preconditioning step, or is it more in the Jacobi step?
For the eigenvalue problem, yes, this is a big issue, is that if you want to, okay, if we're interested in computing the eigenvalues to double precision, then using matrix multiply in quadruple precision dominates the computation, because we don't have at the moment
I
access to fast matrix multiply in higher precision.
I see.
We've done our timing in Julia, and that is a problem. Maybe we should look at other programming language, but in Julia, well, MATLAB either, as well, it's slow.
What about for the SVD? Is it the same or?
No, so for the SVD, it's a bit more encouraging. Okay, maybe not for double precision, but for the single precision. Well, it's there on the slide. We are as fast as the Jacobi algorithm in LAPAC.
Right. So what does that mean? Is it saying that the preconditioning step is not so expensive?
No, because the matrix multiply is done in double precision,
Right,
and that's
right.
fast. Yeah, that's
Okay,
the
that makes
reason.
sense.
So we
okay.
can do matrix multiply in quadruple precision fast, which could be in principle, yes. Then yes.
Thank you very much.
Just another slight philosophical question.
Mhm.
That is that this all assumes that the chip makers are working in our interest, whereas they're not. And
No.
So we would love chips that had quadruple precision in hardware. And you're saying they're just about to take away our double and our single as well. So I presume somebody's going to try and fight back, because there must be many scientific applications for which that's important.
Okay, do we need to fight back is the question. I don't think we need to. I think we need to embrace what's given to us now. And we need to rethink our numerical algorithms, in particular, if we can implement. So in my case, what I need is fast matrix multiply. And I think they can be done, they can be emulated in lower precision.
Emulated, would that mean running very, very slowly?
No. So there's new schemes. In particular, there's this Ozaki scheme. It's not an easy algorithm, but it can run matrix multiply in integer arithmetic extremely fast. So, okay, most of the computation, so the n-cube computation is done in integer arithmetic, and then everything is accumulated in double precision at the end, but that is really fast, and I think that's probably the future. No, it's already implemented in the latest NVIDIA GPU.
I have a question. You mentioned that when, like, one of the bottlenecks is compute, like when you compute a precondition IQ in lower precision, then you have like this, it's not orthogonal at the computing precision. So is it possible to use GMRSIR, like to apply a, like you solve like your orthogonal, you apply the orthogonal projection, so Q times Q transpose Q inverse. So you solve such a, you apply this operator, and when you need to solve, you apply a in a GMSIR fashion.
Yeah, so with GMRS, we need to have a linear system to solve, and there's no linear system to solve. It's applying, it's matrix multiply.
Well, you have the inverse of Q transpose Q, which is not identity, right, in the computed precision.
Yeah, well, our Q is orthogonal, but to certain precision.
Yes, but
We don't want to invert it, really. We could solve lots of linear systems in a way, yes, but do we want to solve n linear systems?
because at least that would give you a like transformation that is that preserves the eigenvalues.
Yeah, I suppose.
But that would be useful.
I think that might be too expensive.
Okay.
I think there are better ways of doing that, but yes, why not?
All right. I guess that's it for the questions. It's three, sorry, three. So let's thank Fran.
Thank you.
Yeah. This.